So you have a reaction at equilibrium, right? So how do we know a reaction is at equilibrium? Look at the arrows. The arrows tells us this is at equilibrium. So the idea behind Le Chatelier's principle is, number one, you have an equilibrium, okay? And number two, you'll disturb that equilibrium. So it's some sort of disturbance. Right, so there's three ways you can disturb an equilibrium reaction. So this reaction is at equilibrium, so it is sort of settled. Either it's settled, this way, more products than reactants, or this way, more reactants than products, or whether it's 50-50. All of that is determined by K, the equilibrium constant. Right, so it's some disturbance. How do we disturb this equilibrium? There's three ways. One, you can increase or decrease the concentration of reactants or products. Increase or decrease the reactants or products, their concentrations. Okay, the concentration of the reactants or the concentration of products. Okay, number two, you can increase or decrease the pressure. This is only when you're talking about gases. Okay, so if you see gases, like in this problem we'll do together, then you have to worry about, are you changing or altering the pressure? So you can increase or decrease the pressure. That's the second type of disturbance. Right, so I want you to realize when they're talking about pressure, we are really talking about gases. Okay, and the third thing you can do to disturb an equilibrium, the third thing you can do is you can increase or decrease the temperature. So these are the three disturbances that can happen when a reaction is at equilibrium. So when a reaction is at equilibrium, you can increase or decrease the reactants or products. You can increase or decrease the pressure, or you can increase or decrease the temperature. Okay? So these are disturbances. How will the disturbance affect this equilibrium? How will it? Okay. So if I push you, what are you most likely to do? You'll push back. Okay, so this equilibrium will revert or go back. Okay, it will go back to offset the disturbance. So that's what Le Chatelier's principle really is about. It's about going back to remove the disturbance. Okay, so it will offset the disturbance. It will offset the disturbance to an equilibrium reaction. So you push back, okay? I push back, okay? So that it gets back to the original equilibrium, okay? It's really as simple as that, okay? If I push you, you don't just stand there, okay, and with your hands up, okay? You push back, and that way we reach an equilibrium. All right, so let's go over three problems to try to make more sense of this. Okay. So predict whether the reaction will shift left, shift right, or remain unchanged after each disturbance. So that's the only thing in Le Chatelier's principle. It'll either make more reactants, make more products, or do nothing at all to reestablish equilibrium. Okay, we are interested in reestablishing equilibrium. Okay, reestablishing this equilibrium. All right, so let's look at this reaction together. 2KClO3 is at an equilibrium with 2KCl plus 3O2 gas. And I want to bring your attention here, something that's very tricky that could throw you off. Okay, so what do we not really care about in an equilibrium? Solids, okay? They don't go into the equilibrium expression. They don't. Okay? All right, with that being said, let's do part A. This is our equilibrium. Okay, what disturbance are we going to do to this equilibrium? Okay, we will remove O2. So think about this. If you remove O2, okay, where will the reaction shift? Okay, you're removing O2. So will it shift to the side to create O2? Remember this is an offset. Or will it shift to the side to remove even more O2? This is an equilibrium. Okay? So you push it, it pushes back. You remove O2, it will shift to the side that has O2. So which side has O2? The reactant side or the product side? Okay, product. So will this shift left or right? Okay, so it's going to shift to the right, to the product side, in order to make O2. Why? Because you removed O2 in part A. Okay, you removed O2, so the reaction will go to the side to, replenish the O2. That's the disturbance. It offsets the disturbance by making more O2. All right, KCl is added to the reaction mixture. Okay, KCl is added to the reaction mixture. Okay, so you must remember here that solids are meaningless. They do not participate in the equilibrium. This equilibrium only is oxygen cubed, or if you want to talk about it in terms of pressure, the pressure of oxygen cubed. So since solids and liquids are nowhere to be found in this, okay, what do you think adding KCl to the mixture a solid will do? Okay. It will no effect, or shift left or shift right. It's a solid. Okay. So you would think it shifts left. But remember, KCl is not participating in this equilibrium, so it's no effect. This is tricky, and I can see why someone would say shift left, but it's not in your equilibrium constant, right? All right, in the same regard, what about KClO3? What do you think? It's a solid. You would think you're adding more KClO3, it's going to shift to the right, but is it? Is it anywhere near here in your equilibrium expression? So what's the answer here? Okay, it will not do anything to the equilibrium. It will not shift left or not shift right. I don't think I got it. I'll give you this one. Or I'll scan this. Yeah. Sorry about that. Maybe it's over there. I'll scan it. I'll give it to you. Yeah. Okay. Any questions on this? So if there's a solid here, no effect. Liquid here, no effect. Okay. All right, what happens if you add O2? Where will it shift? Will it shift to the side that will have O2 more, or will it shift to the side that has less O2? Less. Very good. Which side is that, left or right? It shifts to the left. Very good. Left. To the reactant side. Okay. To remove the O2. Okay, that was added. So this is how we do those problems. Okay, so on an exam, you're just going to, do the opposite. Okay. All right, let's do problem number 2 here. Problem number 2 is a little bit more crazy. Okay? All right. Each reaction is allowed to come to equilibrium, and then the volume is changed as indicated. Predict the effect. Shift right, shift left, or no effect of the indicated volume change. All right, so let me bring to your attention here. What are we dealing with? Okay, we're dealing with gases. Okay, so what can you do with gases? You can increase or decrease the concentration, but you can also increase or decrease the pressure. Okay, increase or decrease the pressure. Right? So we have 2 gases here. Okay, we will increase the volume. Okay, so if you increase the volume, okay, what are you doing to the pressure?
Lowering it?
You're lowering the pressure. So if you increase the volume, okay, you lower the pressure. Okay, these are inversely related. Okay, okay, this is called Boyle's law, but that's from Chem 1. So pressure and volume are indirectly or inversely proportional. Okay. So essentially what we're doing when we're increasing the volume, what are we really doing? Okay, we are decreasing the pressure. Okay, this is the code. Volume increased means pressure decreased. Okay. Imagine if you shrink the volume, and imagine if we have class in the closet. Is that more pressure or less pressure? It's definitely more pressure. Okay, we'd be rubbing shoulders against each other. What about the volume? Much, much less. Okay, so having class here, big volume, okay, less pressure. Having classroom in the storage closet, a lot of pressure. Okay, a lot of pressure, but very little volume. So volume is decreased, volume is increased means your pressure is decreased. So if your pressure is decreased, which way will the reaction go? To more pressure or less pressure? You've decreased the pressure, which is the same thing as increased volume. So if you decrease the pressure, which way will the reaction go? To the side with more pressure or the side with less pressure? We'll go to the side that has increased pressure or to the side that has decreased pressure. Increased? You've decreased the pressure because you've increased the volume, right? So which way will it go? It will go to the side that has increased pressure.
Yeah.
So which side has increased pressure? The one that has 1 mole or the one that has 2 moles? 2 moles, okay? So if you decrease the pressure through increasing the volume, okay, the reaction will shift to the side that has increased pressure, more pressure. So which side has increased pressure? The side with more moles or the side that has less moles? More moles is correct. So this will be the side that has more moles. So in this particular case, correct. This reaction will shift to the right. Okay. Product side. Okay, why is it shifting to the right? The right has 2 moles, okay, the number out in front, whereas the left has only 1 mole. Okay, 2 has more pressure than 1. Okay, 2 people in a closet have more pressure than just 1 person alone in a closet. So if you increase the volume, is the same thing as what? Decreasing the pressure. Which way will the reaction go? To offset it? To the side that has more pressure. And yes, you're right, Alex, it's the side, in this particular case, it's shifting to the product, okay, the side that has more moles. Okay, it's going to go to the side that has more moles. Okay, how about this one? Okay, instead of increasing the volume, we'll decrease the volume. What do you guys think? Decreasing the volume is the same thing as what? It's the same thing as pressure is increased. Okay, so if the pressure is increased through decreasing the volume, which way will the reaction go? Will it go to the side that has increased pressure or the side that has decreased pressure? It will go to the side that has decreased pressure. Okay, decreased. I'm hearing jibber jabber. Decrease, increase, decrease, decrease. It will go to the side that has decreased pressure. Which side has decreased pressure? The one with more moles or less moles? Less moles. Which side here has less moles? Okay, I got 2 here, plus 1 here, 2 plus 1, 3 moles of gas here. I got 2 moles of gas. So the reaction will shift to the side that has less pressure, which is less number of moles, which here in this case is left. Okay, good catch. Okay, so the reaction will shift to the side, okay, that has decreased pressure.
So increases the most moles and then decreases the least amount.
Right, correct. This will be the side that has less moles.
So
Go ahead.
So for C, right? Would not move
Right,
the same amount?
correct. And this would be shift to the left, right? Left has 2 moles, the right has 3 moles, it will shift to the left. Okay, this gases is tricky. Okay, it's very tricky. All right, so here volume is decreased. Okay, what's the same thing as decreasing the volume? Increasing the pressure. Okay, as we mentioned up above, if you increase the pressure, which way will the reaction go? To the side that has more pressure or less pressure? Okay, it will go to the side with less pressure, okay? Okay, less pressure means less number of moles. It will go to the side with less number of moles. But as Alex mentioned, which side has less number of moles? This has 2 moles, and how many moles of gas are on the reactant side? 1 plus 1 is 2. So 2 moles on the reactant side, 2 moles on the product side. Which way will this reaction proceed? The answer is no shift. So this is how you do these problems. Okay, the 3-way you can disturb an equilibrium: changing the concentration, adding one or the other, increasing or decreasing it, also increasing or decreasing the pressure. All right, let's do one last problem here. Just to get the hang of this. What do you guys think about this one here? Coal, which is primarily carbon, can be converted to natural gas, primarily CH4, by the exothermic reaction. By the way, we should know this from chapter 11 as methane. Okay. Bless you, the alkane, methane. But anyways, let's go to this Le Chatelier's problem here. Which disturbance will favor, okay, the key word here is favor, methane, which is CH4. At equilibrium. All right, adding more carbon to the reaction mixture. Okay, you think it will shift it to the right, but are you right in saying it shifts to the right? Okay, because it's a solid. This equilibrium expression, if I were to say it in terms of concentration, it would be the concentration of methane gas, CH4, divided by the concentration of H2 gas squared, but I can also do it in temperature. I can also do it in pressure. If I were to do it in pressure, it's pressure of CH4 over the pressure of H2 squared. Okay. So you see here, carbon as a solid has no place in the equilibrium expression. So what do you think your answer would be to part A? No effect. Okay. Okay, no effect. How about adding more H2 to the reaction mixture? Okay, adding more H2 gas. Okay. After you add H2 gas, which way will this reaction go? To the side with more H2 or less H2? Less. So which way will it go? I'm saying it will shift to the right, product side. Okay, to the side with less H2. Okay, how about raising the temperature of the reaction mixture? Okay, raising the temperature. Okay, what do we know about this reaction? Okay, we know that this reaction is exothermic. So can we go back to Chem 1? What do exothermic reactions release? Okay, it releases heat. Very good. Okay, because this exothermic reaction releases heat, heat is also a product. Heat is also a product in this reaction. So now we raise the temperature. Are we adding more heat or removing more heat? Okay, raising the temperature, we're adding more heat. So which way will this reaction shift? To the side that has more heat or less heat? Okay, we're adding more heat by raising the temperature. Okay, it will shift left to the side with less heat or no heat. Okay. Okay. So which disturbance will favor methane CH4? It looks like this one will give you more CH4. Okay. All right, how about lowering the temperature of the reaction mixture? Okay, if you lower the temperature, what are you doing really? You're taking away heat. Good. So which way will the reaction go? It will go to the side that will generate heat, and that is to the right because it's an exothermic reaction. So this also favors CH4. Shift right to the side with heat. Okay. Adding a catalyst to the reaction mixture, part E. Okay, the two things I want you to know about a catalyst is that whether the reaction is exothermic or whether the reaction is endothermic. Okay, this is endothermic, exo. Okay. Oops, sorry. Okay, this is the progress of the reaction on the x-axis and the energy on the y-axis. Okay, regardless, for a catalyst, all it does is lower EA, which is what we're going to call the activation energy. Okay. So the only thing a catalyst is going to do, it will lower activation energy EA. So that the reaction goes faster. Okay. It just makes the reaction happen faster. It makes the equilibrium happen faster. Okay, it makes the reaction reach equilibrium faster. Okay, faster. So if it makes the reaction go to equilibrium faster, is it really shifting anything left or right? Okay, a catalyst will do nothing to the equilibrium. It just makes it reach the equilibrium faster. So one thing you should know, maybe three things you should know about a catalyst. Number one, the answer to part E, a catalyst will do nothing to an equilibrium in terms of shifting it left or right. So the answer here is no shift. Okay, so that's number one. A catalyst will not affect equilibrium. Okay, which is the answer to part E. A catalyst will lower EA. And finally, a catalyst will increase rate constant K. Okay, this is the rate constant. Okay, not equilibrium constant, rate constant. All right, so what will a catalyst do to this equilibrium? In terms of moving it left or right, it will do nothing. Okay, it just makes it reach this equilibrium state, its predestined state, faster. That's all. Okay. So what's the answer to adding a catalyst to an equilibrium? Okay, nothing. Okay, it will not shift left. It will not shift to the right. All right, and then finally adding neon gas to the reaction mixture. What is neon? Where's neon here? I see carbon, which is a solid. I see hydrogen, which is a gas. I see methane, CH4, which is a gas. I don't know. So what do you think neon will do? Okay, it's not even anywhere here. It's not anywhere here. Okay, it will do nothing. Okay. Doesn't even participate in the reaction. It's nowhere near found in our Kc for concentration or Kp for pressure. So catalyst will not do anything to the equilibrium. It will not make it shift right or left or anywhere. Adding something that's unrelated will not do anything. Adding a solid will not do anything. Okay, the only thing that will change if you increase or decrease the temperature, or if you change the gas concentrations by the pressure or the volume, or you add or remove the gas concentrations, right? Or the aqueous concentrations. Okay. So let me just say this before we move on to the next part here. So the only thing that's really affecting your is aqueous, and then the gas, okay, and then temperature. Okay, these are the things that are changing the equilibrium. These are the disturbances to the equilibrium. All right, are there any questions or comments on this? All right, so with that, this is a wrap of chapter 14. So we have the end of the material for the test, and the end of the material for chapter 14. So we'll start chapter 15 later this week. I think what I'll do is I'll go over some practice problems for chapter 14 for our test. So our test is next Monday, so we'll do a little review about 10-15 minutes each day. Okay? So I have some practice problems, so can you pass these out? Are you wanting to leave?
No. I moved seats because I couldn't see.
Oh.
Don't worry, I'll help you.
All right, so some of these will appear on the exam. So let's make sure you know these, okay? And some more, we'll talk about it as we review a little bit each and every day.